Here we're going to take a look at the drug distribution in the bloodstream of, in this case, we're going to talk about morphine. And suppose we know that the dose of morphine is absorbed in the bloodstream at a rate that's proportional to the amount in the bloodstream. So in a sense, we're having exponential decay going on with this particular medication. The first part of this activity talks about what differential equation will we have that would describe this behavior. Now, since we're talking about absorption, so we're going to be talking about the reduction of the drug in the bloodstream, I'm going to express my constant with a minus in front of it, assuming that the constant K will turn out to be positive in the end. So for the first part of this guy, we're going to talk about the fact that if I call my morphine M, the amount currently in the bloodstream, I'm going to say dm dt is going to be minus K times whatever the amount is in the bloodstream. Okay, so this is our differential equation. We've seen this one before. It's really an exponential decay model. If you don't believe me, we can actually use the differential equation solver, and let's show you what we're going to have there. So let's say we go down to differential equation solver. So m prime derivative is equal to minus K times M. My independent variable I'm going to call T for time. Dependent variable is M. Bada boom, bada bing. There you go. So what this is going to say is that the amount of morphine as a function of time is going to be some constant. I'm going to use A, and then times e to the minus kt. Okay, so there's my solution to the differential equation. All right. Now, one thing when we talk about drug dosage and things, you have to remember there's constantly more drug being administered. So in this case, I think the activity suggests that it is. Let me take a look real quick. So this is part A. Part B says, assuming the initial dose of morphine is m sub 0, solve the initial value problem to find m of t. Use the fact that the half-life of the absorption of morphine is 2 hours to find the constant k. So actually, they're wanting us to call this m sub 0, so I'll call it m sub 0. Okay. And we're wanting to find the K, knowing that the half-life is 2 hours. So we'll assume we'll do our time in hours. So in part B, we know that m of 0 is what we're calling m sub 0. And m of 2 is going to be the half-life, so it should end up with half of what we started with. So it's going to be 1/2 m sub 0. Again, half-life. All right, and we're going to use that fact to find k. So let's do that. So I'm going to start by, let me just define this function. Define m of t equal, let me go up and grab this guy. I'm going to copy that part. I'm going to call this m0. Okay. Got that. So what we really want to do is we want this to be true, that 2 hours into it, I'm half of what I started with. By the way, just to let you know, if I type m of 0 there, I get m sub 0. So what I really want to do is I want to solve m of 2 equal 1/2 times m0. And I want to solve this guy for k. And so that's saying that my k should be natural log of 2 over 2. All right. So we get M of t is equal to m0 e to the minus k, which is natural log of 2 over 2 t. All right, so that's what we've got for part B. What we're ultimately trying to do here is determine, by the end of this problem, we're going to try to determine how to set the dosage that we give so that it reaches a steady state of, I think in this case, we're going to try to shoot for 7 milligrams of morphine in the bloodstream. So that's ultimately where we're headed with this. So part C is going to ask us, it says, suppose a patient is given morphine intravenously at a rate of 3 milligrams per hour. Write a differential equation that combines the intravenous administration of morphine with the body's natural absorption. Okay, so in this case, we're going to have an in versus out. So this is what's coming out of the bloodstream, right? The absorption into the bloodstream, and then we're giving 3 in addition to that. So we're going to adjust our differential equation, our rate in minus our rate out. Okay, well, the rate in, we're getting 3 milligrams per hour. The rate out is this, so we've got minus Km. And again, we've taken into account that this is a decreasing by putting a negative here. So in a way, you could say we were kind of adding these guys up. Just one of them happens to be negative. So what we can do now is we can expand this a little bit. Let me put it down here. So this is going to be 3. And then what we're going to do is we're going to put these guys together and get a total. We know what this thing is, right? Because we found K. So this is going to be 3 minus natural log of 2 over 2. Okay, times m. So now if we are looking at this solution, we can say, suppose we solve our dE that says dm dt is equal to 3 minus Km. Okay, what are we going to get? Well, let's do that. So I'm going to say m prime. Okay, what we're doing now is we're factoring in the fact that I'm adding in addition to the regular absorption. So that's 3 minus K times M. Again, independent variables time, T, M. Alrighty, and here we go. So we end up getting the same thing, that M of T. Oops, I'm running out of space there. Let me grab my eraser. All right, so we got M of T is equal to, again, my M sub 0, e to the minus kt, and then this is plus 3 over k, and so we know what k is here, so that's going to be M sub 0, e to the minus kt, and that's going to be plus, if I flip that guy, that's going to be what, 6 over log 2. All right. So that's kind of what the model that we're looking at. Okay, part D. So part D is asking us to find any equilibrium solutions and determine their stability. So remember when we talked about in this case, it would be the dm dt versus m axis plot. We're really looking at the roots of that, excuse me, the roots of that thing. And the idea that if it goes from above to below, it's stable. If it goes from below to above, it's unstable. And we've talked about that in the past. So let's take a look. So we want this slope, this guy right here, we want that guy to turn out to be 0 for equilibrium solutions. All right, so that's going to say what, that 3 is equal to Km, which implies we're trying to find M is going to equal 3 over K. Okay. Now, when we think about this, this is going to have a negative slope. So indeed, when you think about this as a line, think about this as y equals 3 minus slope times x, right? So it's a negative slope, so it's going to be going from above to below when it crosses the x-axis. So this is going to be a stable equilibrium solution. Okay, and so here we get, oh, this was the same thing we just had. So here m is going to be 6 over log 2, which is approximately equal to, let's compute that, 6 divided by log 2. What did I do? Yeah. So it's about 8 point, we'll call it 66. Okay, so we've got an equilibrium solution. So if we were to graph this guy, it would actually look like 8.66. We'd be kind of moving down toward this horizontal, because remember, we're talking here slope. So we're forcing the slope to be 0. So this would be like, horizontal field lines. Okay, so that's what we're approaching. So it's kind of leveling off to about 8.66. Okay, these would be milligrams in the bloodstream. All right. Okay, part E says, assuming that there is initially no morphine in the patient's bloodstream, solve the initial value problem to determine M of T. What happens to M of T after a very long time? So we want to find out what our M sub 0 is here. So let me let me define that. I'm going to redefine my function M to take into account this other piece that I've got right here. So I'm going to do plus 6 over log 2. All right, so we've got that. We know what K is, so let me define that guy. So menu, define. I'm just going to tell the machine to define K. There it is. All right, so now it knows what that is. And so we're trying to find our initial condition is that there's nothing in the bloodstream whatsoever. Right. So if, let me find it here. Let's solve M of 0 equals 0 for the only thing we don't have at this stage in this expression. We know this because we know what K is. We need M sub 0. So I'm going to say M0. Okay. And so M0 turns out to be minus 6 over log 2. Okay. So our new function then, if we fill in all the information we have, is going to be minus 6 over log 2 times e to the minus I'll go and put K in there. Log, whoops, K, where's my K? Okay, is log 2 over 2. T. Okay, so I've got that, and then this piece here is going to be plus 6 over log 2. All right. So now we kind of have everything we need to know about this function, and we can start to describe its behavior. Okay, assuming that there's no morphine in the patient bloodstream, solve the initial value problem to determine M of t, which we've just done. What happens over a very long period of time? So we're really looking at the limit of this guy as t goes to infinity. So let's take this guy's limit as t goes to infinity. M of t. And we get that, which is kind of what we knew would happen. So again, is at 8.66 milligrams of morphine in the bloodstream. All right, so part F is saying, all right, suppose I know from a therapeutic standpoint that I really want eventually to get 7 milligrams of morphine stabilized in the patient's bloodstream. So at what rate should the doctor reduce the intravenous drug rate so that it is eventually 7? So remember, we started with an initial rate of 3. Where was that? Right here. So what we're wanting to do is we're wanting to adjust this guy so that dm dt is, let's call this my initial rate, okay, and everything else stays the same. So when you think about where this initial rate, where this 3 was in all of the solution process, we can actually go back through all the algebraic manipulation that we've done at this point and just replace the 3's that we had everywhere. Remember, there's a 3 in this 6. Okay, the 6 is really a 2 times a 3. So all this work, we don't necessarily have to redo it all. We can just kind of replace what we had. So our M of t is going to be, okay, this coefficient represented, this 6 was really 2 times the 3 that we started with. So my M sub 0 here is just going to be minus 2 times my initial rate over log of 2. All right, e to the minus, again, log 2 over 2t plus, this turned out to be 2 times my initial rate. All over log 2. Okay. So what we really want to have happen here is we want to be able to adjust this rate so that I'm like kind of leveling off, so to speak, at 7 instead of this 8.66. Okay, so that's our goal here. So that's going to say, squat down here just a little bit. Starting to lose a little bit of space here. So we know that this initial rate is governed by this differential equation. So we want slope. We want the equilibrium solution to be 7. Okay. So let me move up here just a little bit. cordon this off just a little bit here so I can see. So what we need is this slope to be 0. That's going to be the horizontal field line. So that means that r sub I is going to be k times m. If m is to really head to 7, then I can actually use that here to say that my initial rate is going to be k, which in my case was, I think it was log 2 over 2. Yep. Log 2 over 2 times 7. And here I've actually already got k defined, so I just said k times 7. And you'll see that I get 2.426. Okay. So my initial rate, I think it's in milligrams. Yep, milligrams. Milligrams per hour would be what I would want, which makes sense because when you think about it, when we were having a rate of 3 here, okay, we were ending up with a stabilization of about 8.66. So I would need to reduce the amount if I want to have a stabilization of 7. So here we can actually come up with how to adjust the dose so that we end up with the stability we desire in the bloodstream for whatever therapeutic reasons. It might be this particular patient has certain characteristics where 7 milligrams is desired. And so here we can make that adjustment. So this is kind of the idea of how differential equations can be used in a variety of different ways, in this case in healthcare.